Welcome to my video course on AI application for railway signaling. In this explainer, we're going to break down exactly how AI is actually integrated into modern rail infrastructure to boost both capacity and safety. You see, global transport demand is just skyrocketing right now. And honestly, simply laying down more tracks, that's just not going to cut it anymore. We absolutely have to make our existing networks smarter, more resilient, and, well, far more efficient. So let's explore exactly how this incredible technology is being deployed on the tracks to make that happen.
Here's a quick look at our agenda for today. First up, defining AI and signaling. Second, we'll look at narrow versus general AI. Third, we'll cover the core AI capabilities. And finally, number 4, the sense, decide, act loop. Let's get right into it.
Starting off with Section 1, defining AI and signaling, specifically looking at cognitive functions in our infrastructure.
So, what do we actually mean when we say AI in this industry? Basically, artificial intelligence here is defined as a machine's capacity to execute cognitive functions that we'd normally associate with the human mind. We're talking about perceiving the physical environment around it, reasoning through some incredibly complex operational scenarios, learning from past events, and problem-solving right on the fly. The absolutely crucial point to remember is that AI, in this context, is less about building fully autonomous, unsupervised systems that just run wild, and it's much more about granting machines specific cognitive functions. Why? To enable better, faster decision-making between humans and machines.
That brings us to Section 2, narrow versus general AI, which is really all about managing our expectations. Before we get too carried away, it's vital to understand that all railway applications today utilize what's called narrow AI. This means they're built to perform highly specific tasks, mostly because they completely lack the overarching common sense of a human being. For example, a system might be absolutely brilliant at analyzing a video feed to detect a fault on a rail switch, but it can't suddenly decide to rewrite the staff schedule. On the flip side, we have general AI, or strong AI. These would be machines capable of solving lots of diverse, unrelated problems totally independently, just like you or I would. But it's super important to remember that this type of strong AI does not yet exist. We are firmly living in the era of narrow AI, mastering specific, high-value tasks.
Okay, moving to Section 3, let's look at core AI capabilities, or the actual mechanics of smart signaling.
To make train control truly smart, cognitive signaling systems basically rely on 4 fundamental capabilities working together in a sequence. We've got perception, reasoning and decision-making, learning, and finally, actuation. This specific framework is exactly what takes a static, reactive piece of infrastructure and completely transforms it into a dynamic, predictive network. Let's break down exactly what each of these means for the future of train control.
The very first capability is perception. This is where AI utilizes advanced sensors, think cameras or lasers, to visually identify tracks, signals, and any potential obstacles in real time. Just imagine a setup with highly sophisticated audio and visual sensors constantly sweeping a level crossing. The AI can instantly differentiate between, say, a vehicle blocking the tracks, which obviously triggers an immediate safety reaction, and just a piece of blowing foliage, which it knows it can safely ignore. That right there is perception in action.
Next up comes reasoning and decision-making. This is where the system analyzes all that perceived data to actively determine the future state of the environment. It calculates the safest, most efficient path, and it does it without any human delay. Think about it. If a train is delayed, the system can rapidly simulate literally millions of options in the background, figuring out the absolute best sequence for trains to pass each other. And it does all this while making sure these proposed changes don't inadvertently create massive bottlenecks somewhere else in the network.
The third capability is learning. This means these systems continuously adapt and improve their accuracy over time by taking in new operational data and feedback rather than just relying strictly on handcrafted static software. By processing vast amounts of historical schedules, weather patterns, and real-time sensor data, the algorithms actually refine their own predictions. They literally learn from experience, allowing them to make better routing and maintenance choices tomorrow than they did today. Finally, we have actuation. This is the system's ability to actually impact the physical world based on all that reasoning we just talked about. This could look like an automated braking system engaging, or maybe a robot deploying to patrol the perimeter. It's the execution phase, right? The system doesn't just suggest a smart solution, it has the capability to physically alter the operational environment to maintain both safety and efficiency.
And that brings us to Section 4, the sense, decide, act loop. Seeing AI in action. So this is what we call the sense, decide, act loop. AI software agents continuously cycle through perception, reasoning, and actuation to completely optimize control and predictive maintenance across the entire network. This loop is constantly synthesizing data from the outside environment, as well as the health of the railway assets themselves. By acting as this continuous, real-time feedback loop, the system can minimize those rigid safety margins we're used to and proactively shape traffic flow. And the result? Drastically reduced delays and a massive boost to overall network capacity.
But here's the thing. Because these narrow AI systems can't operate completely unsupervised, we really have to ask ourselves, how will our human roles adapt to safely collaborate with this powerful technology? Today, AI might just act as an advisory tool, but as it scales up, humans are going to have to shift from manual, click-by-click routing to high-level strategic supervision. That human-machine partnership, it's absolutely the ultimate key to unlocking the true potential of our future mobility networks.
As we transition from rigid, reactive tracks to highly predictive cognitive networks, the technology itself is pretty clear. But it leaves us with one final, provocative question. As AI takes the wheel for routing and safety, is our rail industry culturally prepared for humans to step back from the controls and become strategic supervisors? It's something to think about.